Okay, gentlemen, today is Tuesday, May the 12th, and today we are going to continue our discussion of about waves, and we're going to do this and specifically talk about sound waves. All right, now your ears right now are picking up sound. Now that sound has been transferred from my voice box to my computer through the interweb somewhere, and it's coming out of the speakers on your phone or computer or wherever you happen to be watching me right now. All right. How exactly does that sound travel? Well, excluding all the electronic stuff, the computer to server to back to computer, whatever, right? When sound travels, it travels as a wave. All right. Now, specifically, sound is a mechanical wave, and it requires a medium to travel through. In other words, sound will not travel through outer space. Okay, it will travel through air. It'll travel through water. It'll travel through any solid material, wood, metal, earth, you name it. It will travel because those things act as media for the sound. Now, the study of sound is called acoustics, all right? And you've heard that word before. We talk about acoustic guitars and all that kind of stuff. And essentially, what an acoustic guitar is simply one that's not generating the sound electronically. It's generating the sound naturally, acoustically. Now, sound itself is what we call a longitudinal mechanical wave. And so instead of this, remember, is a transverse wave. A longitudinal wave is something like this. You have a medium, and I'm going to try to evenly space the medium out. And what happens is if you push this piece, well, it goes here. Notice how there's a spot where it's closer together now, and so here to here, and then the next one it's going to be here, and then here and here, and so on. And so essentially the sound wave is moving in this direction through the medium. And so when I speak, I push a little air, and that air pushes the next molecule of air, and that molecule pushes the next molecule, and that molecule pushes the next molecule. All right, and it works as what we call a longitudinal wave. Now, what happens here is that an oscillation in the pressure of the medium, in this case the air, causes the molecules of the medium to collide, and that transmits the wave. But the sound itself is not moving the medium. The sound is simply the energy of the vibrating medium moving from one place to another. Now, the velocity of sound in a given medium depends on the density of the medium. In air at standard temperature and pressure, the velocity of a sound wave is 331 meters per second. All right, but at standard pressure and room temperature, the velocity of a wave is 343 meters per second. Now, this information is found on your handy-dandy reference tables. I had a set of reference tables sitting here on my desk, and I cannot find it right now. Oh, there it is. But on the very front page of your handy-dandy reference tables, you have the speed of sound in air at STP. All right, and so it's located right there. And you'll see it's 331 or 3.31 times 10 to the 2th meters per second. So it's there. All right, it's there. Now, it turns out, and this may be counterintuitive to some of you, but sound actually travels faster through liquids and solids than it does through gases. And the reason for that is that the liquids and solids are denser. They have more molecules in a given unit of volume, and therefore there's more collisions between those molecules, which actually transmits the sound wave faster. If you've ever watched an old Western movie, the cowboy will put his ear down to the railroad tracks to determine whether a train is coming. All right, and that's not just because you can't hear it in the air. It's because the sound travels faster through the rails than it does through air. Just like any other wave, sound can be reflected. All right, if you've ever stood in a valley and yelled out your name, hello, you can hear the sound of your own voice echoing back at you. That is a reflection, right? The reflection of a sound wave. It can also be refracted. If you talk through something like a mask or your hand, all right, the sound wave is distorted, right? Because what's happening is that as it passes through that other medium, it's changing its direction. That's refraction. And sound wave can also be diffracted, meaning that it can be spread out. All right. We'll talk about diffraction a lot more when we get to light. Sound waves can also interfere. All right. Just like the transverse waves that we talked about a few days ago. When two sound waves come together, they can either amplify each other or they can cancel each other out. A very famous example of that occurs in the U.S. Capitol. Back in the old days, the congressmen and senators used to have desks right in the middle of the rotunda. This was before they built rooms for the House of Representatives and the Senate on either side. And it turned out that, and I never remember the story exactly, but I think it was Adams and Jefferson. It was two politicians who were on opposite sides of the political aisle. And one realized that he could hear everything his opponent was saying from the other side of the room, even though they were whispering. And that was because the sound waves were going up into the rotunda, being amplified, and then bouncing back down. And so he could hear everything that his opponent said. Now, as a reminder, before we talk about the next aspect here, V equals F times lambda. In other words, the velocity of a sound wave is equal to its frequency times its wavelength. And the wavelength is the distance between the regions of maximum pressure. All right. And so if you have sound waves traveling through a medium, all right, this distance, notice these two are close and these two are close. Excuse me. This distance, is one wavelength. All right, one wavelength. Oh, goodness. So what does that mean for us? Well, it brings us to a very interesting aspect of sound called the Doppler effect. Now you're asking yourself, what exactly is the Doppler effect? And the explanation in words is relatively long, but I'll try to illustrate this a little bit later on. The frequency of sound, all right, that's the pitch, depends on the oscillation frequency of the source. All right. Now, the source can be your voice, it can be a car horn, it can be a fire whistle, whatever. If the source is moving, then the wavelength of the wave will change, and I'll show you this in a minute. If the object moves toward a sound detector, like your ear, more waves will be crowded into the same space, and so the wavelength will decrease. Now, because the velocity of a sound wave is constant in a given medium, the sound detector, your ear, registers this as an increase in frequency. Okay. Now, the Doppler effect is easily demonstrated, and you've all experienced it before. All right. There's a CSX rail line that runs literally right behind my house. And so, somewhere between 20 and 60 times a day, big old freight trains go running through. All right. And as they go running by, you can actually hear the pitch of the sound that they make change. All right. If you've ever watched a NASCAR race, same kind of thing. If the microphone is sitting right next to the track, as the car goes past it, it goes, and the sound literally changes its frequency. Right? It gets higher and higher and higher and higher until it reaches the microphone, and then it goes lower and lower and lower as it moves away from the microphone. Right? This is the Doppler effect. And essentially it has to do with how fast the waves are moving. So let's say, for the sake of argument, that this is a train. All right, I'm looking at it from the top, okay, and it's moving in this direction. Actually, let's just do a train for the moment that's, whoops, not moving at all. All right, and so let me get rid of that and that and that. And so in this case, if this thing is producing a sound, then the sound is going to radiate, and I'm going to try to draw perfect circles here, but it's never going to happen. And so here's the sound waves getting further and further away, kind of like the ripples in the water on a pond if you've dropped a rock in them. And each of these distances, this is one wavelength, and this is, well, should be one wavelength. Now, on the other hand, if the train is moving, okay, then, and it's moving in this direction, so it's moving forward, the locomotive itself, whoops, the locomotive is actually going to catch up with the sound waves in front of it. And so what you're going to, whoa, Betsy. What's going to happen is this. The sound waves are going to start looking like they're elongated, and you're going to catch up to the sound waves in front of you, but the ones behind you are going to get further and further away. I know this is quite the exaggeration, but notice the wavelength here is much smaller than it was over here with the non-moving train. And the wavelength here is much greater than the wavelength of a non-moving train. And so here, the wavelength goes down, and therefore the frequency goes up. And over here, the wavelength goes up, and so the frequency goes down. Okay. Now, the same thing. Well, actually, we'll leave it at that for now. All right. And so, even though if you were riding in the train, you would hear no difference in the sound. All right, it would remain the same. And it's only if you're standing on the side and you're listening to the train that you hear this increased frequency as it approaches you, and a decreased frequency as it moves away. All right. And so if the source moves away from a sound detector, like your ear, the perceived frequency decreases. If it's moving toward the sound detector, then the perceived frequency increases, like we said a couple of slides ago. Now, interestingly enough, the same thing is true if the source is stationary, but the detector is moving. So if you ride your bicycle or drive a car past a blowing firehouse, a whistle on a firehouse, all right, you will actually experience the same effect, even though the whistle is staying stationary and you're the one who's in motion, right? And again, it's just a perception of the frequency of the sound that you're listening to. Okay, now let's talk about some of the characteristics of sound. We have, the first one is going to be the idea of pitch. All right. Whoa, that's awfully quick. Pitch is the frequency of a sound. So it's you know what the differences are in pitch, right? For example, if you speak in a very high voice, Elmo likes physics, right? That is a high-pitched sound, right? On the other hand, if you speak in a very deep voice, and Obi-Wan is your father, right? Then you're decreasing the frequency of that sound. Now, this is for those of you who are musicians, I was going to say magicians. I knew that wasn't right. But for those of you who are musicians, you experience this in the musical scales. All right. Now, the scales themselves were elucidated by the same Joe Pythagoras who gave us the formulas for a right triangle. What he found was that two notes whose frequencies are related by a ratio of 2 to 1 are an octave apart. All right. So, for example, if this is the middle C, okay, that for crying out loud, then this is also a C, because notice 128 hertz is 1/2 of 256 hertz. And 512 hertz is also a C, all right, because this is 512 is twice the frequency of 256, all right, and so every octave in the on the musical scale is a doubling of the frequency or the pitch of that particular sound. All right. Now, the last thing that I want to talk about here in terms of sound waves is loudness, all right? The loudness of a sound is essentially its amplitude. It's the amount of energy that you put into the noise, all right? If you whisper, the amplitude of the sound is very low. But if you shout, then the amplitude of that sound is much higher. Now, amplitude in sound is measured in a unit we call decibels, all right, decibels. And decibels are units of sound abbreviated with a lowercase d and an uppercase b. The b is actually for bells. I can't remember the guy's actual name. But in any event, that's the unit. Now, decibels are actually given in a logarithmic scale, and the scale ranges from 0 to 120 decibels in terms of loudness. Now, 0 decibels is obviously imperceptible. This is no sound at all, and 120 decibels. 0 is the threshold of hearing. 120 decibels is the threshold of pain. This 120 decibels is essentially when your ears start to bleed. All right, 120 decibels is the sound of an aircraft jet engine firing up. That's why everybody on the runway is wearing ear protection, right? And 0 is the threshold of hearing. Anything lower than that or smaller than that is not going to be able to be heard. Now, normal conversation, like the conversation that I'm having with you now, right? Although you can change the volume on your phone or computer or whatever it is, but normal conversation is about 70 decibels. When I'm teaching in class, I'm probably a little louder than that, and so it's probably somewhere between 72 and maybe 73 decibels. All right, 80 decibels would literally be 10 times louder than normal conversation, and so I'm certainly not that loud when I'm talking in class. All right, and so again, this is a logarithmic scale. So 80 decibels is 10 times louder than 70. 90 decibels would be how much? 100 times louder, right? That's what a logarithmic scale does. All right, it's not 20 times louder; it's 10 times louder. Or 100 times louder. Anyway, so that's the idea here. So 20 decibels is literally a 20 decibel noise is literally 10 times louder than a 10 decibel noise. Not twice as great, but literally 10 times as great. All right. 20 decibels is not 2 times louder than 10 decibels. It's 10 times louder than 10 decibels. All right, 10 to the 1th versus 10 to the 2th, essentially. Okay, so, and of course, 30 decibels is 10 times louder than 20 decibels. All right, gentlemen, that brings us to the end of our discussion on sound, at least for now. We will come back to this later on. But for now, happy Tuesday, and I will talk to you tomorrow.